Hello, and welcome to this Smiths Interconnect webinar. My name is Katie, and I will be your Global Spec moderator, and I would like to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. Just to the right of the main presentation window is the speaker bio window with background information on today's presenters. The large window with the heading Presentation in the upper left is the primary window for today's webinar. And just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now let me introduce today's presenters. With us today is Mike Shire. Mike is the Product Line Manager of Filters and Integrated Filter Assemblies at Smiths Interconnect. Also with us today is Sean Adams. Sean is an RF engineer at Smiths Interconnect. To read more about either of our presenters today, please look at the speaker bio window right next to the main presentation window. And with that, I'd like to pass things along to Mike to get this webinar started. So Mike, go right ahead.
Thank you, Katie. We're excited to talk to everyone today. My name is Mike Schweier, and I am the Product Line Manager for RF Filters and Filter Subassemblies at Smiths Interconnect. Joining me is Sean Adams, an RF Design Engineer for RF Filters, also at Smiths Interconnect. I will be discussing the applications in the X, KU, and KA bands and the challenges of optimizing the RF filter and reducing the size. We'll discuss the materials and processes to attain these filters, and Sean will go into detail on the results. I'd like to start out with a survey question for the applications in these bands. If you have applications in the X, KU, or KA bands, which market segment are you predominantly serving? Commercial, industrial, defense, or space? I'll wait a moment for you to provide an answer. I understand that there may be overlapping markets, so please provide the segment that is the more dominant. Okay, I'll just give it just a few more moments here. Okay, here are the results. Defense is a large part at 64%, followed by industrial at 14%, and commercial at 14%, and finally at space at 7%. This is what we see at Smiths Interconnect as well, so it's good to have the feedback. Thank you for that. The radio spectrum in the microwave frequencies is commonly segregated by the IEEE radar band designations. These bands designations cover the spectrum from HF up to millimeter wave or G-band. This webinar is focusing on 3 specific bands, and I'll discuss why these bands are of interest. The first band I'd like to discuss is the electromagnetic frequency band from 8 to 12 gigahertz, known as X-band. This corresponds to wavelengths of 3.75 to 2.5 centimeters. Due to the small wavelengths, this band is predominantly used for radar applications, particularly for civil, military, and government applications. This band also has applications in terrestrial communications and satellite communications. The KU band has wavelengths of 2.5 to 1.67 centimeters and comprises the electromagnetic frequency spectrum of 12 to 18 gigahertz. This band is primarily used for satellite communications, particularly for the downlink. The SATCOM communications include direct broadcast, deep space communications, and marine very small aperture terminals. Finally, covering frequencies of 27 to 40 gigahertz is the KA band. Due to the very small wavelengths of 11.1 to 7.5 millimeters, Applications in this band include very high-resolution radar. However, like the KU band, most of the applications are with satellite communications, but more often for the uplink. Now I will get into some detail on the X-band applications. As I stated, there are many applications within this band, but I'll highlight radar applications in particular. There are many applications for radar in this X-band, including weather, air traffic, and defense applications. The radar systems operating in this band often use multi-mode active electronically scanned array or IESA systems. These systems can use hundreds to thousands of transceivers in their systems. These systems must limit size and weight to remain practical. One of the enabling technologies for radar applications in this band is the high power available with GaN mimics. The other components required to support the transceivers operating in the X-band also need to be small and cost-controlled to support these radar systems. The RF filters are needed in the up and down converters in these systems, as well as other areas. They are needed to filter out harmonics and subharmonics generating during the frequency conversions for the systems to have sufficient signal-to-noise ratio. The overall performance of the system is directly impacted by the signal conditioning of each of the channels. Satellite communications have been moving to higher frequency bands to increase data transfer rates compared to communications in lower bands. Actually, there are a lot of reasons to consider before choosing a band for satellite communications, and there are advantages and challenges for each band. Besides increasing the bandwidth as you increase frequency, antenna sizes decrease as well, which are both advantageous. One of the challenges is with the atmospheric attenuation of signals due to rain, sleet, or snow, also known as rain fade. The attenuation of electromagnetic energy due to water vapor does increase with higher frequencies, and there are some wavelengths that have significantly high attenuation. This is one of the reasons why the K-band was segregated into the KU, or K under, and the KA, or K above bands, as the center of the K-band has very strong attenuation from 18 to 27 gigahertz. Rain fade is also a factor of frequencies above around 10 gigahertz. Performance, reliability, size, and weight are critical factors with satellites. There are trade-offs that are mitigated with the system designs. The RF filter design has many options in this frequency band. Would the larger size of a cavity filter undermine the lower insertion loss and improved rejection? Could other areas within the RF chain compensate for some of the loss with a significant reduction in size and weight? I'm sure there are arguments for both options, and it likely depends on the mission, expected life, and budget for each satellite. Reliability is another factor that is mission dependent. One thing to note is the less complex the component, generally the higher the MTBF, or mean time between failure. Reliability can be increased with additional screening and qualifications of the components and or the system. Finally, I will discuss the KA band applications, and a large segment is again found in satellite communications. There are discussions on the proponents of KU versus KA bands for SATCOM, with valid points to be found for both. One factor to consider is the higher attenuation due to rain fade. This signal attenuation is compensated by additional power, so many times the uplink or terrestrial to satellite transmission is KA band, and the downlink or satellite to ground station transmission is KU band. The additional power to transmit to a satellite is obviously more readily available on Earth. They both allow for data rates in the terabits per second and are used commonly in the low Earth orbit constellation satellites. KA band leads to smaller antennas as well. When considered satellites operating in this frequency, the constellation satellites typically have a lower life expectancy and are more cautious to cost. One way of reducing costs is to reduce the screening and qualifications required. The trade-off of the benefit of full screening against the cost savings of limited or sample screening is more common for the KA band. The performance of the RF filter is another key decision in the overall system. Waveguide filters do become smaller with increased frequency, but are significantly larger than printed filters in this band. The improvements in low noise amplifiers in this band makes the smaller size of the printed filters much more attractive. I would like to discuss the importance of the RF filter in the applications I mentioned earlier. Presented here is a simplified block diagram of the RF front end of a transceiver. The transceiver uses a local oscillator to downconvert the received signal to an intermediate frequency, or IF, and converts the intermediate frequency to the transmission frequency. The signal processing takes place on the IF, and the information is modulated in the transmit and receive signals. The RF filter is a key component of the system. It removes interfering signals in the receiver and any harmonics generating in the mixing of the signals and the LO. Without the filtering, the range and performance of the transceiver would be very limited. Based on the importance of the RF filter and the applications described, one can understand the importance of how size and weight of a filter correlates with the cost. Whether it is the amount of fuel required to launch a satellite into orbit or the overall weight of a transportable radar system, size and weight are significant factors in the overall system design. However, the performance of the filter must be sufficient to support the overall system demands. Our Planar X series of bandpass filters offer a good solution to address the swap-C market demand. They offer significant reduction in size and weight, but with excellent performance. My colleague, Sean Adams, will review this in more detail soon. In order to meet the market demands using the KU band, the printed filters need to be very small and controlled geometry. One method to attain this is with thin film processing, which can support geometries as low as 10 microns. The filter is designed on a low-loss tangent substrate with a high relative dielectric constant. The pattern determines the filter's response, and the metal used must be highly conductive for low loss. Thin film provides a repeatable pattern by using a high-precision photolithography to pattern a light-sensitive photoresist through a mask of the filter design. The typical process is laser pre-drill for creating the vias and edge wraps, a DC sputtering of the metals, the photolithography and etch, and finally the dicing of the substrate to the individual filters. Okay, and now I will introduce Sean Adams, the RF filter designer, to provide a detailed discussion on the printed filters. Sean, the floor is yours.
Thanks, Mike. So here I'd like to take a minute to pose another survey question. When selecting an RF filter for your application, what is the most important characteristic you're concerned with? I'll just wait a moment for everyone to lock in their answers. Don't worry, there is no weakest link in this webinar. Also, don't blame me for the preposition at the end of that sentence. I'm just the messenger here. Give it a couple more seconds here. So performance, okay. If you said performance, you're almost certainly looking for a cavity filter. These types are large when it compared to other topologies, but have best-in-class insertion loss, power handling, and selectivity. If you chose any of the other three options, printed filters would be the answer. These types of filters boast the smallest sizes, cheapest costs, and can be found in distribution unless you need a custom solution. So a good spot to start when discussing printed filters is to piggyback off of Mike's swap-C analysis. If size wasn't an issue, printed filters would have no market value. However, due to the cost, weight, and size constraints, the need for a different type of technology exists. In steps the printed filter and thin film processing. This technology allows for a significantly reduced footprint and weight when compared to other filter topologies. Due to the wide array of different substrate options, these filters can be designed for quicker time to market, smaller sizes, or lower losses. Substrate selection plays a vital role in how small or large a filter will be, as well as what frequencies will be possible. When getting into frequencies even higher than the ones we're focusing on in this webinar, quartz with a dielectric constant of around 3.8 will be essential. In contrast, when dealing with lower frequencies such as C-band, a type of titanate may prove to be the best choice with a dielectric constant around 38. There are even some substrates with dielectric constants above 100, but these materials generally have inferior loss tangents, which contribute to higher losses in circuits. Before we dive into some standard solutions and how they compare with other types of filters, I wanted to go over some options and technologies that these printed filters lend themselves to. Like many other filter technologies, printed filters can be lumped into certain categories. Band passes, low passes, high passes, bandstop filters can all be realized in planar solutions. Band passes can then be separated further into edge-coupled, hairpin, and interdigital, to name a few. These different types of printed filters can be customized to fit almost any next higher assembly, and using state-of-the-art tools such as AWR Microwave Office and HFSS, these custom solutions can be prototyped to meet competitive time-to-market timelines. With printed filters, just like every other filter technology, the designs must follow a rigorous design process to ensure efficiency and compliance. After receiving specifications, a feasibility analysis is performed. It is during this stage where we determine what type of topology or technology a filter would need to be. If a specification comes in with kilowatts worth of power needed or ultimate rejections below 100 dB, we know printed filters will not be the solution. However, when it is determined a printed filter can be used based off of size constraints and practical losses, we then move to filter synthesis and 2D analysis. Here we establish what kind of resonator geometry is best suited for the specification. Whether it be half wavelength, quarter wavelength, or even a type of hybrid or dual mode structure, the decision is based off of a variety of inputs. First is coupling bandwidth. If the filter is narrowband, half wavelength structures allow for asymmetrical responses and quicker time to market life cycles than other geometries. As we start to get into more wideband responses, quarter wavelength resonator structures must be used. There are of course, some trade-offs between the two topologies, where half wavelength resonator structures produce a symmetrical response. These resonator geometries produce a much more selective high side of the filter. This is due to the parasitic coupling introduced when resonator structures are placed in line and close in proximity. This type of filter does shrink the size, but needs a plated via for each resonant structure. Once the 2D analysis is done and substrate thicknesses and resonator geometries are roughed in, we move to a more precise 3D analysis. Using a finite element method of simulation, we are able to optimize the circuit and its geometry to ensure we are as close as possible to meeting the initial spec when the thin film process is done. The most important step in the process comes when the design is nearly complete. Once the geometries are optimized and the filter is meeting specifications, a tolerance study or a Monte Carlo analysis must be performed. This test exposes any flaws the design may encounter from different lots and tolerance stackups. There are thousands, if not millions, of different responses the printed filter may exhibit, from geometrical tolerances to dielectric constant tolerances. Every version must be simulated to ensure compliance of every filter. So to minimize costs and expedite timelines, we ensure popular bands are covered with standard filters. These bands were strategically chosen, as Mike demonstrated, based off of our customer and industry needs. Due to the surface mount nature of these devices, they are ideal for pick-and-place applications and systems where size is the #1 priority. Due to the low loss tangent and dielectric constant, these 3 standard filters were processed on 99.6% aluminum. We use a ti-palladium base layer, then metallized with gold for its non-corrosive and low loss properties. So as you'll see when we dive deeper into these specifications of these filters, there are some trade-offs between planar filters and larger cavity filters at these frequencies. The first on our list is the X-band printed filter. This particular variant is centered on 10 gigahertz and has an equal ripple bandwidth of 4,000 megahertz. Boasting a small footprint of 0.4 by 0.18 inches, the X-band printed filter has a typical loss less than 2.5 dB over most conditions. A theme you will see throughout the typical standard microstrip filters is that they will struggle with ultimate rejections when compared to the cavity filters. This is due to the inline nature of most printed filters. It is difficult to isolate inputs and outputs along with different resonant sections within the filter. If you were to design a typical cavity filter at this frequency, due to the percent bandwidth, you'd likely go down the route of an interdigital cavity. The size of this particular unit would come out to be around 1¼ inches long and 0.7 in width. It would also come with about a ½ inch of height, making it almost 4 times larger than the printed filter version. While it does come with losses of 0.6 dB and slightly better attenuation levels, some systems at this frequency simply cannot deal with the size or weight of the cavity version of this filter. At roughly 11% of the cost of a typical cavity filter at this frequency, pricing is likely a large factor when considering a printed filter in this band as well. Similar to the X-band version, this planar filter in the KU band utilizes a quarter wavelength resonator structure due to its relatively wide bandwidth. This particular filter is centered at 15 gigahertz with an equiripple bandwidth of 6,000 megahertz. Here we see typical losses of around 1.5 dB in most environments, with close-in rejections at 30 and 40 dB. Like the aforementioned filter, its counterpart in a cavity-style topology is again an interdigital filter. Clocking in around approximately 1.2 inches long and 0.6 inches wide, the cavity style is about 5 times larger. Due to materials and labor, the printed filter in this band is about 20% of the cost when compared to its cavity version. Though the cavity filter bests the planar style and insertion loss and close-in rejections, the weight, size, and cost makes it unfit for most applications in this band. And for the last of our comparisons, we see our KA band planar X bandpass and a typical waveguide filter in WR28. Here we see the biggest reduction in size at nearly 80 to 90%. Trade-offs will come in the form of higher losses and lower rejection levels for the planar X style of filter, but another benefit which can be attributed to the previous 2 planar style bandpasses come in the form of far less assembly and testing time. Coupled with the fact that while the cavity and waveguide filters need to be tuned, these microstrip filters come in with no tuning needed, which significantly impacts the price to the tune of a 90% cost reduction in this particular instance. So in order to guarantee these types of filters can withstand the necessary conditions, they must be thoroughly qualified, which is why we've chosen to derive our qualification test flow based off of Smith Interconnect's legacy space heritage. The flow chart displays the types of tests that will ensure consistent performance under harsh environmental conditions. We split the testing into 3 different groups. Under Group A testing, we find internal and visual inspections in accordance with IPC A600, along with room temperature RF testing before and after temperature cycling. Group B testing will consist of fewer parts undergoing more rigorous environments. It is at this stage we will test at the temperature extremes and introduce the unit to vibration and mechanical shocks. Group C will consist of even further units and will be split up into endurance and destructive subgroups. The endurance portion will see the units tested at different altitudes and humidity levels, while the destructive and most entertaining subgroup will find the limits of a particular filter. Here we subject the unit to different power levels and temperatures until we see a destructive failure. But this slide represents a KU band custom filter we qual tested a couple years back. Here we get to see in more detail the methodology and conditions of tests we run on our planar filters. Of course, if a customer had different needs and specifications, that would always take precedent over our proposed testing. So as we wrap things up here today, I just wanted to briefly sum up what we've covered. Mike covered the 3 bands of interest, X, KU, and KA band, that we're finding to be the most in demand at the moment. And due to the proliferation of satellites and radar, the atmosphere and low Earth orbit are becoming increasingly congested. This pervasiveness prevents the need, even more so than before, for high performance, low cost, and exceedingly small RF filters. This presents new and challenging opportunities for RF engineers and will usher in new technology and materials. I would be remiss at this time if I didn't mention our online tool, Filter Select Plus. This application allows the user to define certain parameters such as insertion loss, center frequency, bandwidth, and rejections to find a filter that will suit their needs. Currently, only products including discrete parts, ceramic filters, and cavity filters are available, but be on the lookout for a new and improved version including our line of printed X or planar X printed filters. Well, now it's time for that inevitable product push. Shown here is our catalog of filter topologies we specialize in. We offer RF tunables from 24 to 3000 megahertz, cavity filters and waveguides ranging from 30 megahertz to 40 gigahertz, cost-effective ceramic resonator filters ideal for surface mount applications with frequencies from 400 to 6,000 megahertz covered, along with discrete filters between 5 megahertz and 10 gigahertz that can be arranged in bandpass, low pass, high pass, or notch configurations. And last, thin film planar filters up to 40 gigahertz. We also have some of our Planar X thin film bandpass series filters we talked about today, soon to be in distribution. We also specialize in custom solutions for demanding applications, and our sales and engineering teams are always looking for new opportunities to partners with customers large and small. I'd like to thank everyone that joined us today and open the floor up to some questions.
All right. Mike and Sean, thank you both so much for that great presentation. So Sean, as you just mentioned, we are going to start taking some questions from our attendees. For our attendees, if you have a question today, go ahead and place it into the Q&A window and click Submit. We will do our best to answer as many questions as we can. If you don't hear your question being answered, do not worry. We will reach out to you following today's webinar. All right, gentlemen, our first question today. What is the biggest driver for choosing a Planar X solution in these frequency bands?
I'll take that, Katie. I would say that the number one driver is the volume. When you get to hundreds or thousands of filters required in some of these systems, the lower cost and smaller weight and size really is the most impact when we're talking about larger quantities like that.
All right, thank you so much for that answer. So another one here. How accurately do you control the dielectric constant in your high K material?
So I can answer this one. So we usually have a tolerance of about plus or minus 1 for something that is around a 38 dielectric, which we most commonly use. And we can always simulate and run Monte Carlo analysis to make sure that each variation of that dielectric will pass over the temperature extremes.
All right, thank you so much for that answer. Next one here. Photolith has over and under cutting when etching. What can you achieve?
Well, it kind of depends on the metal stack up and how thick of a metal you use. So it's there is ways to control by annealing the metals, to avoid some undercutting. But there's other things that can be done as well. But it's I guess I can't give an exact answer just because it depends on the thickness, the overall thickness.
Okay, thank you so much for that answer. For our attendees, you can use that Q&A window to submit your questions. And I also just wanted to point out while I'm here, the resource widget located under your Q&A window. There's a lot of great resources listed in there today. So if you'd like to take a moment to grab those before we end the webinar in a little while, that would be ideal. We also have a survey along the bottom of our attendee console, and your questions and feedback are appreciated for that survey. So please take a moment to take a peek at all of the widgets located along the bottom of your webinar console. All right, gentlemen, our next question here. Through holes vias are laser cut or drilled. What about surface metallization impact?
I can answer that one. Typically, you laser drill. So you use a laser to pre-cut the holes before metallization. So, and there's processes like bead blasting, for example, that make sure that any kerf or anything that's generated during the laser processing is removed. So it forms a very, very solid, very good adhesion.
All right, thank you so much for that answer. Next one here. Is external matching required for the filter via transition?
Yes, so I can take this one up. There really is no matching required for the filter via transition. We have a proprietary fixture that we test all these filters on. So we actually are able to match into whatever 50 ohm trace that you may have. So as long as your trace is 50 ohms, there would be no external matching required.
All right, thank you so much. So next one here. How long to develop a filter to the customer's design, and is tuning required to meet the requirements?
So I can take this one. Obviously, a timeline would vary depending on the complexity of the spec, but usually we can, make a filter that passes all the specifications in about 16 weeks. And no tuning is required to meet the requirements. These come in completely tuned.
All right, thank you so much. Next one here. What about filter reentrance at 3 times the center frequency?
Sure, I can take this one as well. Most of these actually probably will have a reentrance before 3 times the center frequency, but we can cascade low-pass filters to cover up anything that happens to pop up at those frequencies.
All right, thank you so much for that answer. We have another question here. Is the launch in and out suitable for wire bonding or soldering?
I can take this one. Absolutely, we can do. We have a metal stack up that's suitable for soldering, and it is also wire bondable.
All right, gentlemen, thank you so much. For our attendees, if you don't hear your question today, do not worry. We will reach out to you following the webinar. And for anyone that has a question, go ahead and use that Q&A window and click Submit. So, gentlemen, next one here. Will the additional loss in the Planar X solutions impact the overall system performance?
Mike?
I'm sorry, I'm having a little bit of I'm sorry. Absolutely. With the newer game technology that's going through, the cost of having the additional gain is much lower than it was just several decades ago. So the benefits of the smaller size and the smaller footprint are greatly used in this. Thank you.
All right, thank you so much for that answer. So we have time for a couple more questions today. If any attendees have any last-minute questions, go ahead and place it into the window and click Submit. All right, gentlemen, the next one here. What are the lead times for custom Planar X solutions?
So again, I would say this varies a lot on the specifications, but we can usually hit it around 16 weeks, perhaps a little bit longer if it needs a Rev 2. But yeah, I would say around 16 weeks.
All right, thank you so much for that answer. And this is going to be the last question that we're going to take today. If any attendees have questions that we haven't answered yet, do not worry, we will get back to you. And if anybody has a question they'd like to ask, you can enter it into that window and we will get back to you following today. So gentlemen, the last one for today. What kind of power can the Planar X filters handle?
Yeah, so again, this typically varies based on, bandwidth of the filter and the type of topology that we would use. But usually printed filters are low power devices, around 1 watt. We have seen, actually the one that we tested where we showed you the methodology of the test report, that one actually started to get destructive around 20 watts. That was a narrow band filter. So if you had a wide band filter, and we could absolutely do up to 50 watts, I'd say. But typically these are low power 1 watt devices.
All right, thank you so much for that last answer. So as I mentioned, we are going to start to wrap things up right now. I would like to say a huge thank you to Mike and Sean for a great presentation and for answering some of our attendees' questions. So gentlemen, thank you both.
Thank you.
Yep. Thank you, Katie.
Okay, and for all of our audience members, I did mention the resource widget once already, but there are some great items in there that you can take with you today. Please take a moment to go through our resource widget and grab everything on your way out. And just a note that you will be receiving an email from us with a link to the on-demand version of this presentation. You will be able to come back and watch this again at any time over the next 90 days. And lastly, I did mention this earlier, there's going to be a survey that will appear on your screen at the end of this webinar. For anybody watching this webinar on demand, that survey will be located along the bottom of your attendee console in the survey widget. If you could please take a moment to fill that out. Your feedback is always important to us. Again, thank you for taking time, everybody, to attend this webinar event. Take care, and we will speak with you soon.